my presentation of the layer of the Earth. Today, we're going to explore the internal layers, composition, depth, and unique characteristics. Understanding these layers is crucial for grasping how our planet works and how it impacts life on Earth. So, let's get started. The Earth is made of four main layers: the crust, mantle, outer core, and inner core. Each layer varies in composition, depth, and together they create the dynamic planet we live on. First one is crust, the outermost layer where we live. It's relatively thin and consists of solid rock. The second one is mantle. Beneath the crust, the mantle is much thicker and made of semi-solid rock that flows slowly. The third one is outer core. This layer is liquid and composed mainly of iron and nickel, generating the Earth's magnetic field. And lastly, the inner core. The innermost layer is solid and extremely hot, also made of primarily of iron and nickel. It is a thinner layer, averaging about 5 to 70 km deep. The rocks found in the mostly of lighter elements such as silicon, potassium, and sodium. The density of these rocks is about 3 times that of water. There is two types of crust: continental crust and oceanic crust. Continental crust. The continental crust, which is 35 km thick, is most composed of less dense rocks than the oceanic crust. Some of these less than these rocks, such as granite, are common in the continental crust, but rare is the oceanic crust. Oceanic crust, thinner and denser. This crust lies beneath our oceans, which is 5 km to 10 km thick, is composed primarily of basalt, diabase, and gabbro. The crust is where all life exists, and it's composed of various rocks and minerals. It's also where we find natural resources like fossils, fuels, and minerals. This is an example of crust. Next, we have mantle, which extends about 2,900 km deep. It occupied about 84% of Earth's volume. Mantle, it's about applied to the rock shell surrounding the core of the other planets. In the solar system, the Earth's mantle is the only one that is continually active and is divided into upper and lower mantle. The upper mantle. The upper mantle is the layer of the Earth located beneath the crust and extending to a depth of about 410 kilometers or 255 miles. It's primarily composed of the solid rock, including minerals like olivine and pyroxene. This layer is further divided into lithosphere, which includes the crust, and asthenosphere. The lower mantle. The lower mantle is the layer of the Earth located beneath the transition zone of the upper mantle and above the core mantle boundary. It extends from a depth of approximately 660 km or 410 miles to 2,900 kilometers to 1,800 miles beneath the Earth's surface. This region is characterized by high pressure and temperature and is believed to be composed primarily of silicate minerals like Bergenmeer ferropericlase. This is an example of mantle. Now, let's talk about the outer core. It's a liquid layer of the Earth's interior situated between the mantle and the inner core. It's primarily composed of the iron and nickel, and its high temperature and low viscosity allow it to flow, creating the Earth's magnetic field which protects us from harmful solar radiation. This is an example of outer core. The inner core is the Earth's innermost layer, a solid sphere composed primarily of iron and nickel. It is incredibly hot with temperature ranging from 5,200 degrees Celsius to 6,000 degrees Celsius. Despite the high temperature, the immense pressure, estimated to be 3.6 million atmosphere, keeps the inner core in a solid state. This is an example of inner core.
We've managed to go hundreds of thousands of miles into space. But when it comes to the Earth, we've barely scratched the surface. Our planet's core is a magnificent mystery filled with secrets. Well, it's time to figure them out. The Earth's inner core is an extra hot solid ball with an approximate radius of 760 miles. To put that into perspective, it's just 30% smaller than the Moon. But if we've never been there, how did we find this out? Well, we've learned about the core by observing the effects of gravity on objects on the surface of our planet. From there, it's estimated that the Earth's mass is 5.6 sextillion tons. Get out your bathroom scale. Nah, don't. The density of everything that lies on the surface is much lower than the core's average density. Scientists figured out that most of the Earth's mass is located towards the center of our planet. It's estimated that more than 80% of the core consists of one of the 10 most common elements in our galaxy, iron. But the iron on the Earth's surface is kind of limited. I know what you're wondering. How did the iron make it all the way down to the core? Well, there is a simple explanation. The heavy element somehow pushed itself, literally, towards the center of the Earth. And a ton, pardon the pun, of research was done to figure out how. Most of the Earth's surface is made of rocks called silicates, and the molten iron had some difficulty passing through them. To help you understand, think of how water struggles to get through a greasy surface. But in 2013, Wendy Mao and her team from Stanford discovered a possible solution for how this happened. They began an experiment to see how iron and silicate react when they're exposed to extreme pressure, like that in the core. They used a diamond anvil cell to pinch the two substances under those conditions, and they achieved it. The pressure was 330 gigapascals, which is around 3.3 million times the atmospheric pressure of our planet. The molten iron slowly squeezed through the silicate rocks, and they had their answer. It took millions of years for the iron to reach the center, so it happened at a snail's pace. Since snails weren't around back then, the iron had to guess how fast to go. Well, now that we have that figured out, how do we know what size the core is? That's when seismology comes into play. During an earthquake, shock waves are spread through the planet. Seismologists study these vibrations and try to read the reflections on the other side. It's like Thor is hitting one side of the planet with his hammer, and the seismologists are listening from the opposite end. But these vibrations also take different routes. They go through various parts of the planet, and that affects the sound they make at the end. Let's take a small detour for a minute. Seismology is quite an old scientific field. In the old days, when vibrations occurred, scientists noticed that something was wrong with them. These vibrations were S waves, and when they were supposed to show up on the other side, they just vanished. At first, they thought that something was wrong with their equipment, and it just wasn't picking up the vibrations. But as science progressed, it turned out that these picky S waves could only go through solid material and not liquid. So, something molten was present in the center of the Earth that was preventing the vibrations from going through. So they started digging into their data. They mapped out the paths of the seismic waves and found that around 1,860 miles from the Earth's surface, the rocks transformed into a liquid. But there's also an interesting fact in the game. Inga Lehmann was a Danish seismologist, and in the 1930s, she discovered a new wave pattern. First, we had the S waves that didn't pass through liquid, but then there were also P waves that could travel through the core and appear on the opposite side of the planet. That was when Inga came up with a theory that the core has two layers. The solid inner core, which is around 3,700 miles below the surface, and the molten outer core, which is around 1,860 miles below our feet. When advanced seismographs were invented, her theory was confirmed, but that took 40 years.
Finally, we reach the inner core. This layer is about 1,200 km thick and is solid due to the immense pressure. Layer by layer. The first one is crust. Location, outermost layer. Thickness 5 to 70 km. State solid. Composition silicate. Density 2.7 to 3.0 degree or centimeter cube. Temperature 700 degrees Celsius. The second is mantle. Location beneath the crust. Thickness 2,900 km. State solid flow. Composition silicate. Density 3.3 to 5.3 gram or centimeter cube. Temperature 500 to 400 degrees Celsius. The third one, outer core. Location beneath the mantle. Thickness 2,200 km. State liquid. Composition iron and nickel. Liquid. Density 9.9 to 12.2 degree gram centimeter cube. Temperature 4,000 to 5,000 degrees Celsius. And the last, the inner core. Location, center of the earth. Thickness 1,220 km. State solid. Composition iron and nickel. Density 12.6 or 13 gram or centimeter cube. Temperature 5,000 to 6,000. And that That's the fascinating structure of our planet. Form the thin crust we live on, the scorching, solid inner core deep below. Each layer plays a vital role in shaping Earth's geology, magnetic field, and even light itself. Understanding this layer helps scientists predict natural events like earthquake and volcanic eruption and give us an insight into how our planet has evolved over billions of years. Thanks for watching. I hope you now have a clearer picture or amazing layers that make up our planet. Bye!